years or 5 years down the road, they might say, but now all of our guys don't use radios, they use cell phones, or we use Nextel, or we use something else, or something else. And so the owner of the building has to be responsible for adapting the system to meet whatever frequencies might be required. All right, so as we go through this, I'm going to run long. I was told I was okay to run a little long, so sorry. All right, so the secondary power, fire alarms, we're used to fire alarm panels having 24-hour standby power, but it's not on all the time, right? This is on all the time. So this is 24 hours of standby batteries for something that's powering up amplifiers and things that burn a lot of energy for 24 hours. That's a lot of batteries, right? So that's in a NEMA-rated enclosure. It's got to be waterproof, right? It doesn't work well, but it's got to be in a waterproof cabinet. Big batteries in a waterproof cabinet means that you don't have a lot of venting, right? So you get a lot of hydrogen that can build up in there, which creates risks associated with that, right? And then, like I said, the additional frequencies or changes of frequencies, the owner has to adapt the system for those. But you can still use the other stuff, right? The fire function. Most of the systems have to be designed ahead of time and submitted for approval prior to being installed. You have to have a license, right? It's an FCC device. It means you have to have a radio license. The companies that are putting these in need to be licensed and qualified on how to do that. Now this is, I know full well nobody's going to read that, right? You're already going, David was right. There's a ton of words on there. But this is the part that's the conflict. That all you need to care about is the 90%. Now for testing it for acceptance, all they're asking for is 90%. But then for re-upping it and getting the permit, it's got to do 95. So you can build a system terribly and then a year later it fails. So you don't want that. Right? So this is something that we need to all do a public input to their code committee to say, change that to 95 or change everything to 90, but make it consistent, whatever you think. And then it's got to comply with the FCC because if the thing, like I said, if it starts broadcasting, then the FCC is going to figure out where it's coming from, and they want to know who's responsible so they can get it fixed. So that doesn't work. So some of the components, if you look, you've seen in hospitals and you've seen in different areas of shopping malls and at the airport and stuff, you'll see these little antennas sticking out. Those are the distributed antennas that look out. You know, if they're being used, that's what they look like. They stick out of the ceiling. You have amplifiers in the background. You've got you can use the leaky RF cable, the radiating antenna cable that can be in a very skinny building, certain areas. It can broadcast and balloon out and work. This is a diagram of how it would work. There's two schools of thought. There's active and passive. When we talk about distributed antenna systems, active versus passive. And I think that if you don't understand the difference, passive is pretty much most of the systems that get put in. You have a donor antenna up on the roof of the building. It's aimed, it's a Yagi antenna, so you can see it's a directional type of an antenna. And it aims at the tower of the first responders, where they have their radio tower. So you get that signal back and forth, and it transmits and receives two different frequencies through that same antenna. And it goes down through the building, it gets distributed through these amplifiers and stuff, and then you put these little antennas in the building as needed to make sure the signal goes everywhere. That's a passive system. Has amplifiers, has different components associated with it. An active system is different in that it has a head end in place, and maybe it has a data link or something. Instead of radio getting into the building, it has a data link that feeds in from the municipality somehow, or it has the ability to have cell phone coverage in there, or whatever types of systems that they want, comes in and combines out and uses that same antenna system to broadcast throughout the building. And it can be campus-wide. You can run fiber between buildings and you can distribute it that way, and you get less loss in the cabling that way. So it's a very flexible system, but it can be a lot more expensive, more complex. So active versus passive, most people will accept passive, and passive usually works just fine. So that's what we see. These are the frequencies, in case you weren't familiar, these are the frequencies of first responders around the U.S. This is the FCC defines these frequencies, and so you'll have very high frequency, which seems pretty high, but there's a higher one, and that's the ultra high frequencies, which is UHF. And so they have different frequencies. One in the San Jose document, if you look it up, they are actually saying that they want 700 megahertz also. Just throw that in there. They just go, oh yeah, well we want all this in the gray box there, but we kind of want 700 megahertz too, and we're kind of thinking about going to 800 megahertz down the road, so make sure it does 800 megahertz too. Good grief, that's a lot of equipment to try to guess about, right? And so if you've ever put these things together, as you add frequencies, you're adding money to that system. So, these are just things to think about. Again, other places will say, I don't want any cellular frequency coverage, I only want these in the gray box, that's all I want. So it varies, and that could change. So things to think about is being flexible in the design of this thing, so that the customer isn't hung out, having to spend a bunch of money and tear out what they put in and redesign it. This is kind of an RF map, kind of a heat map. There's a company, if you want to make a note from an engineering standpoint, IB Wave, it's the letter I, letter B, and one word wave, ibwave.com. They have modeling software that can be used to do the modeling of the radiation of how you put the antennas together. So they can do the design up front, help you do that kind of stuff, but there's software associated with it. You can load drawings into it. I don't think you can load them models in it, but that's probably at some point they will. This will kind of show you, the hot areas are good, the cold areas are bad, so this may tell you in this area of that office you might want to have to put a distributed antenna, reroute them around to figure out how it's going to work. But it's a custom solution, right? Because every building is a little bit different. This would be a 3D view of that, what that IB Wave stuff can put out for you to let you know, from a plan view or from 3D rendering, what that looks like. Again, you have a bidirectional antenna. You have a signal back and forth for that system to work. But, like I said, if you have an AHJ that allows it, it certainly could be an ROI for an owner to be able to have cell phone coverage in a building everywhere, in addition to having just emergency stuff, right? They hope no emergency ever happens, but they want to use cell coverage all the time. So if you can get it to work with the AHJ, there's some value for an owner to do that. And so I would explore that as an idea when you do the designs to see if that's a viable option. And then you look at that as a VE, you say, okay, give me the price for this and give me the price for that, and that way you can see if it makes any sense or not. We don't make these, by the way, so it's not a shameless plug for actually. But secondary power, something to think about for supervision. Power, 24 hours of standby time. There was a really good reference material in NFPA 1 in 2009 that had Annex O. Annex O talked about